3.1 Exponential Functions. We're beginning our chapter on exponential and logarithmic functions. A lot of this chapter is going to be review, so that'll be a good thing, a review from Algebra 2. Evaluate exponential functions, graph exponential functions, talk about, again, that base E, and compound interest formulas. Okay, so first of all, the definition of an exponential function. An exponential function is not just something that has an exponent. We have had polynomial functions. That has exponents with it. Rational functions sometimes have exponents, but an exponential function is a function where a number is your base. That's what b represents, and then x is actually in the exponent. There are some conditions for that base, and in the definition of exponential function box, you can see that the base has to have a value greater than 0, and it cannot equal 1. And x can be any real number. That'll have implications for our domain a little bit later, but I want to offer you a bonus, those of you who are viewing this. Why do we have these restrictions on b? And more specifically, what happens to the curve if b is equal to 1? And what happens if b is less than 0? Answering those two questions will help you answer that bonus. Why the restrictions? There's going to be a Desmos link here in a little bit that might help you explore those kinds of questions. Okay, so let's talk about Objective 1, Example 1, evaluating an exponential function. I'm not going to spend a lot of time on this, okay? If you read through the question, you can pause to take a second to do that. But basically, we have an exponential function. Our base is the 1.56. And we want to know what is the average amount spent, that would be in dollars, after 4 hours. It also says there, notice, to the nearest dollar. So we might have some rounding to do. So x is our time. And if we take our function and we put in 4 for our time and we approximate, that would be approximately $250. I would want that dollar sign on your answer there. Okay? All right. Let's get on to graphing exponential functions. This is where you'll spend most of your time on the Math Excel homework, and then in your groups you'll talk about graphing as well. So we're going to have two different ways to graph exponential functions. One way is to use a table. With polynomials and quadratics, we wanted to say, let's figure out more about our function. Where are the turning points? Where are the zeros? What is the end behavior? And let those things help us decide which x's to put in our table. For exponential functions, we always take those x's around the y-axis. Okay, so specifically, we have a rather large table here, going from -3 to +3 as far as the x's go. You will not always do 7 points. We just want you to see the 7 points now, so you can get an idea of what the behavior of the exponential function is. We will scale that down to 3 points as we go. Okay, so filling out our table, if x is, and when you look at this, I would recommend looking at it from the +3 up to the -3. If x is +3, then y is 8. So the point 3, 8 will show up, and 2, 4, and 1, 2, and 0, 1, and -1, 1/2, and -2, 1/4, and -3, 1/8. I want you to spend some time letting your mind think about, why is it that when x is +3 you get 8, and when x is -3 you get 1/8. Okay? So we plot those points and we connect the curve, and we have that J-shaped curve that you remember from biology. Okay? Exponential functions do have a horizontal asymptote, like rational functions sometimes did. Exponential functions, it's not a sometimes, it's an always. Okay, so our basic asymptote for exponential functions is going to be the line y equals 0. And that's the x-axis. You see it dashed in here. That's the horizontal asymptote being dashed. You're going to be asked for that in your Math Excel assignment. You're also going to be asked, wait a minute, let me back up. Remember from Chapter 2, when you enter a horizontal asymptote, make sure you say y equals and the number that your horizontal asymptote is. Okay, if you don't put y equals, Math Excel will not count it as correct, and it shouldn't. Okay, let's talk domain and range. Before, on the definition of an exponential function, remember on that page it said x can be any real number. Any real number for x is an all real numbers negative to positive infinity kind of domain. Okay? The range, on the other hand, is not all real y values. This horizontal asymptote, the graph curves down and levels off at or toward y equals 0. So all of our range is going to be the y values above 0, which we could say y greater than 0, or you can see there the interval from 0 to infinity. Notice that the 0 has a parenthesis on it and not a square bracket. Okay, the parenthesis on the 0 is because the y value never actually hits 0. Okay? All right, let's take a look at one more of these. Graphing 1/2 to the x power. Okay, so still you'll make a table. I haven't shown the table, but feel free to pause this and make your table and jot your points down and then play. You need to pause now if you're going to. So we get this picture from a table of values, -3 to +3. You can see that those are the points they used because that's where they have shown these distinct x values, the distinct ordered pairs. The domain still stretches left forever and right forever. The horizontal asymptote is still y equals 0, and the range is still 0 to infinity. Okay, the difference though, let's look at that again. The difference is that this function is what we would say is an increasing exponential function. It rises as you go to the right. Okay, but this one is a decreasing exponential function, meaning that it falls as you go to the right. Okay, the reason for that we'll explore here in just a minute. Okay, so I mentioned a Desmos link earlier. Here it is. I'm going to go ahead and activate that. Okay, sorry for the load time. All right, so I made this, and again, you can go to that link that's on the other page and you can explore and play with this as well. Okay, so what we want to know is what happens, why is it that some exponential functions increase and some decrease. So if we just play this really quickly, see how now it's decreasing and it's gone now. Oh yeah, because b can't be negative. And it's decreasing and now it's increasing. Where does that changeover happen? Where does it go from increasing, which it still is increasing, and it's still increasing now, it's just increasing not as quickly. When does it switch? Did you see it? Remember the acceptable values for b? b couldn't be negative, but b also couldn't be 1. 1 is where the switchover happens. Right now it's decreasing, now it's increasing. Decreasing, increasing. Okay? Again, you can go to the link and you can play with this if you would like. Okay, so you have this graph in your textbook that kind of shows a basic example of what I was using Desmos to show you. And you can use it also to help you know when does it increase and when does it decrease, to help you work that out in your own mind. Let's look at this table and we'll see if it gives us a clue as well. So different characteristics, just basic characteristics of any exponential function, or your basic parent exponential function. The domain is negative to positive infinity for every one. The range is from 0 to infinity. And that is because y equals 0 is your horizontal asymptote. That can change from problem to problem. The domain will not change. Okay, y-intercept is an important point. You can see over here on this diagram that all 4 of these curves have the exact same y-intercept. Okay, remember y-intercept is the y value when x is 0. And if you take any base to a 0 power, you're going to get 1. So 0, 1 is the y-intercept for every basic exponential function. We're going to talk about transformations next, and when it transforms, the horizontal asymptote can move, and so can the y-intercept. There is no x-intercept. It never touches the x-axis. All right, so if b is bigger than 1, if our base has a value that's larger than 1, even if it's a fraction or a decimal, if that fraction or decimal is greater than 1, then our function is going to increase. Like the green, y equals 7 to the x, or the black, y equals 2 to the x. Those increase. They get steeper as b gets bigger. But if you have a function that the b value is between 0 and 1, like 1/2 x and 3/4 x, that actually decreases. And the closer the b value is to 0, the steeper the decrease. Okay. Couple more. 5b to the x exponential functions, those are one-to-one functions. And that's going to be important for us later this chapter. Okay? A one-to-one function means that your curve will not only pass the vertical line test, but it also passes the horizontal line test. Okay? Again, we'll go back into that later in this chapter. All right. Talking about the horizontal asymptote here. As b of x gets closer, goes out on the one side, it will get closer to the x-axis, but it does not touch it. It approaches it, but does not touch it. That creates this horizontal asymptote. Okay, you might have to go back and watch that again. Hopefully it'll become more clear as you're working the Math Excel. Remember, you can come back and watch this as you work the Math Excel. That page wasn't supposed to be there. Okay, you're now ready to work the first 5 questions on your Math Excel assignment. It goes with textbook questions 11, 17, 19, 21, and 23. Those are your first 5 questions. Okay, so feel free to stop this now, go work those, come back to the video, timestamp 13 minutes. All right. The second way we can graph is with transformations. We just got done talking about transformations with rational functions. We did transformations with quadratics. We looked at it back in chapter 1, which was page 213. If you would compare the chart that I have here, which is in your textbook for 3.1, with the chart on page 213, it's going to look so much the same. Okay, so we have the basic transformations. We have the vertical translation, or slide or shift, which comes from adding or subtracting a value, and I will say outside of the function. Outside of an exponential function means that it's something that you have the b to the x, and then you add the c, or then you subtract the c, or you have the number in front, and it's plus the b to the x. But it's addition or subtraction that's not really involved in the b to the x. On the other hand, the horizontal translation is when you are adding or subtracting within the function. And within an exponential function means in the exponent of the function. That will shift to the right or to the left. It's the opposite still of what you expect it to be. The reflection, 2 kinds of reflection. One is the vertical reflection, and that's when the negative is multiplied to the function, meaning negative times the b to the x. Okay, some of you may be looking at this right now. I feel a sneeze coming on, by the way. And looking at this and saying, but I didn't think b could be negative. Okay, this b is not negative. This is -1. I'll try to type over here. -1 times b to the x. Okay, so when you see the negative there in front, it is not saying the b is negative. It's saying it's taking a negative multiplied by the b to the x. That causes a vertical shift, so it's going to shift over the x-axis vertically. If you have the negative inside the function, meaning up there with the x, it's going to reflect it horizontally, okay, across the y-axis. And we still have the vertical stretch and shrink, and if you have a multiplier, like in the first example with the shopping, there was a multiplier out front, that's going to cause it to either be more steep or less steep than the parent. And the horizontal stretching and shrinking is a multiplier inside or up there in the exponent. And again, it's going to cause it to shrink in, and it will appear to change its steepness. We have a couple of transformations problems we can look at. Okay, so basically with transformations, think about where we're supposed to use f of x equals 3 to the x. And here we can make a table. It says identify 3 points. I have 4 here. -2, 1/9, -1, 1/3, 0, 1, and 1/3. If we're going to use this graph to get a graph of g of x equals 3 to the x plus 1, we're going to take this 3 to the x function and we're going to shift it. Okay, I want you to think, is it horizontal or vertical shift? Horizontal, because the plus 1 is in that exponent. And horizontal is opposite of the way you think. So instead of shifting it right one, it actually shifts it the left one. Okay? So what you can do is you can plot this in pencil or barely put your point here for 3 to the x and then say, nope, shifting every point to the left 1 unit. Okay, so the orange matches up to the red. Every one is shifted over to the left a single unit. Yep. That's right. It is Friday at 5:30 and I am still at school. Okay. If we are graphing, looking at another one, this is example 5, 2 to the x, to get 2 to the x minus 3, this minus 3 is after or outside. And so we're going to take the 2 to the x function and we're going to shift all of our y coordinates down 3. I want you to notice here that the horizontal asymptote just changed. Instead of being y equals 0, we shifted down 3, so it's y equals 3. Let me page back over here. Did the horizontal asymptote change when we shifted horizontally? No, it did not. But it does shift. It does change when we shift vertically. Okay. I wanted to do one thing. That's right. Okay, so one more thing before I give you your next set of problems. Natural base e, evaluating functions with base e. Remember, e is a number. There's a nice chart in your textbook that shows you where that number actually comes from. It's complicated, but it occurs very much in nature, in populations, in finance. We see this number showing up. Okay? So just like we can graph with a base that's like a 2 or a 3 or whatever, we can graph with the base e. Okay, you can take on your calculator and do e to the first power, and that'll show you that approximation to be about 2.7. Remind me February, so we can do an e day. February, I always forget, February 7th. Okay, so I took the liberty of highlighting some things in this example 6. You should read the whole thing and pause now if you need to do that. But it's talking about this gray wolf population, and it gives us a function that will model the recovery of these animals in the northern Rocky Mountains. So this is specific for this area, okay? All right, so the f of x is the gray wolf population. The x represents years after 1978. So whenever you're calculating that, I want you to think, if I was born in 1978, how old would I be in a certain year? Okay, so Our job is to project the population, so the f of x, in 2010. So, okay, if I was born in 1978, how old would I have been in 2010? Okay, so we would have been 32 years old, and if we solve that, the population would be about 3,412 gray wolves. Okay, with those things under our belts, transformations, and talking about the E here, you're ready to work on 9, 10, and 13 on your Math Excel assignments. These will build. They will ask you for horizontal asymptotes. They will ask you for domain and range. Might even ask you to graph the parent function, the 3 to the x, to get to the 3 to the x plus 1. Okay, so those 9 and 10 especially will be multi-step problems, I know. Okay, coming to the end here. Compound interest formulas. Compound interest, we have two different formulas for compound interest. We have compounding in a discrete way. Discrete means it's countable. I can count how many times we compound. Continuous compounding means it's compounding all of the time. With every beat of your heart, with every breath you take, with every blink, it's compounding. By the way, just thinking about that, that's a good thing if you have invested money. It is a stressful thing if you're the one borrowing the money, but continuous compounding is what your bank's probably going to do. Okay, so you have to, in this case, the things that are consistent is that we're investing $8,000 for 6 years. That's consistent. But we have two different options. We can either compound monthly at 7% or continuously at 6.85%. So this has the higher interest rate, but this is compounding all the time. We're supposed to see which one is the better investment. Let's start with the formulas, and I apologize that these are fuzzy. You can go to your textbook to get a better picture, or just write them down. Over here, compounding discretely, we need to know 4 things. We have to know the principal, that's the money we started with. We have to know the interest rate, the time, but also N is the number of compounding periods. So for us, that's monthly. That would mean N is going to be 12. Okay, so the 8,000 is our P. The rate was 7% over 12, and then 12 times 6, that means 12 compoundings and for 6 years. Okay, we work through that. Be really careful with your calculator. I would do this part, 12 times 6 first, and then do 1 plus 0.07 over 12 to the, I maybe press enter and then do the to the 12 times 6 power, and then multiply that by 8,000. Please make sure that you're getting this 12,160 and 84 cents. Make sure that you're getting that amount. Excuse me. You want to know now if you're entering it into your calculator correctly. If not, we need to check and see what's going on. Okay, so now, is this a better deal, or is compounding continuously a better deal? We have the same P. E is not a variable, it's a number. We have the rate and we have the time. So we have 8,000 times E to the RT power. T is still 6 years. The R is 6.85% or 0.0685. Again, calculate your exponent value first and do 0.0685 times 6. E to that power times 8,000. And you get $12,066.60. So which is the better investment? It's important to remember that you are getting this money, not owing this money. This would be completely flip-flopped if you owed. Okay? Which is the better one? Well, in this case, the compounding monthly at 7% is the better deal. I'm just going to highlight this. That's the better deal. I would want $sign on your answer because this is in dollars. Okay, you're now ready for your Math Excel 11 and 12. Okay, hope you've taken notes. so that you can come back and check those notes. And remember, I'm always here if you need to pop back and check on anything. Remember, you can scroll through the time at the bottom and you can kind of see, okay, where is she? Is she on the problem I need? You don't have to watch the entire 25 minutes over again.